In this video, we're going to look at another example of separable differential equations. An object of mass m falls from rest at time t equals 0. That means the initial velocity is equal to 0 because it's falling from rest. From an initial height of h meters, that means the initial height of the object is h meters above the ground. Assume that air resistance is proportional to the instantaneous velocity of the object. Find the limiting velocity of the object as t becomes large. That means as t goes to infinity. Also find an expression for the height s of t of the object at time t, assuming that ds dt is rate of change of position with respect to time, so that is velocity. ds dt is equal to v of t. Initial velocity is 0 because the object falls from rest. And initial height, s of 0, is equal to h. Now, according to Newton's second law of motion, mass times acceleration, acceleration is the same as dv dt, rate of change of velocity with respect to time. And so mass times acceleration is equal to minus kv, which is the force due to air resistance, minus mg, which is the force due to gravity. And gravity, of course, is 9.8 meters per second squared. And k is a constant of proportionality. We take k to be positive. All right. So what we have is mass times dv dt is equal to minus kv minus mg. Now, let's think about that. Let's look at this diagram. So we have this mass here. The force due to air resistance is minus kv. We're taking the up direction to be positive, the down direction to be negative. When the object is falling, the velocity of the object is negative. So we have minus k times v, but velocity is negative. That means the force of air resistance will be a positive quantity because we have a product of two negative things. Minus k, that's a negative number, and velocity is negative. So the force of air resistance is positive, is in the up direction. We expect that because the force of air resistance is opposing the falling motion of the object. And the force of gravity, of course, is mg, that's downwards. So what we have is mass times dv dt is equal to minus kv minus mg. This is our differential equation. We're now going to separate the variables and solve this. So separating the variables, we get dv divided by minus kv minus mg is equal to 1 over m dt. So that's after doing some algebra, cross multiplying and dividing and all those things. Now let's integrate both sides. So let's do U substitution on the left-hand side. We're going to let u be equal to minus kv minus mg. Note that v is your variable, k, m, and g are constants. Differentiate both sides. We get du is equal to minus k dv. Solve for dv. dv is equal to du divided by minus k. So we have integral 1 over u times dv, dv is du, is equal to du divided by minus k. This is equal to, and integrating the right-hand side, well, integral of 1 over m is just going to be 1 over m times t, because we're integrating with respect to t. We're reversing the power rule, so plus c. Alternatively, you can think of it as we kind of push out 1 over m. It's a constant. We push it out of the integral, and we're just integrating integral 1 dt. That gives us t. And t, let's say, plus c. That's what we're doing. All right, let me erase that. Okay, so now we get negative 1 over k. Negative 1 over k. And what is the antiderivative of 1 over u? The integral of 1 over u is going to be log of absolute value of u is equal to 1 over m times t plus c. All right, so now let's multiply both sides by negative k, and we get log of u is equal to minus k over m times t minus ck. All right, now let's substitute u back in, because u is equal to minus kv minus mg, so we get log of minus kv minus mg is equal to minus k over mt minus ck. Okay, so we have log of minus kv minus mg is equal to minus k over mt. And we have minus ck here, so let's just call it another constant, let's say c2. So plus c2, where c2 is equal to minus ck. Now, we need to get rid of the log, so we exponentiate both sides, and we get e to the ln of absolute value of minus kv minus mg is equal to e to the minus k over mt plus c2. E and log cancel, so we get absolute value of minus kv minus mg is equal to e to the minus k over mt times e to the c2. But e to the c2, we can just call it another constant, let's say call it a. So we get absolute value of minus kv minus mg is equal to a times e to the minus k over m times t. So we apply the exponential law, basically e to the a plus b is equal to e to the a times e to the b. So notice that the constant that was additive becomes multiplicative here, and that's the result of the exponential law. Now let's get rid of the absolute value. We get minus kv minus mg is equal to plus or minus a e to the minus k over m times t. So let's introduce b. B is equal to plus or minus a, and b will be determined from the initial conditions that we have been given. So we rewrite this as minus kv minus mg is equal to b e to the minus k over mt. Now we need to find the value for b. Well, we're given the initial velocity. The initial velocity is 0. The object falls from rest. V of 0 is 0. This means when time is 0, the velocity is 0. Let's plug those in. So we get minus k times 0, because velocity is 0, minus mg is equal to b e to the minus k over m times 0. Well, e to the 0 is just 1, so we get b is equal to minus mg. So basically we have minus kv minus mg is equal to minus mg e to the minus k over m times t. Now we need to do some algebra and solve for velocity as a function of time. All right, so if we do that, we get v of t is equal to mg divided by k e to the negative k over m times t minus mg over k. So that's after we do some algebra to this expression here. You would add mg to both sides and divide both sides by minus k. That's pretty easy algebra to do. So we now have the velocity of the object as a function of time. The question asks us to find the limiting velocity of this object as time goes to infinity. So let's take the limit as t goes to infinity of v of t. Clearly, the negative exponential is going to approach 0. So let's take the lim as t goes to infinity of mg over k e to the minus k over mt minus mg over k. So this negative exponential is going to go to 0, this part here, that's going to go to 0. So the result will be the limit as t goes to infinity of v of t is equal to minus mg over k. This is known as the terminal velocity of the object. Now notice that the terminal velocity, v terminal, is equal to minus mg over k is negative because we chose the downward direction to be negative. Now we have to find the height function, s of t. So we want to find height as a function of time. Well, s of t is simply the integral of the velocity function, and we already have solved this differential equation and found an explicit expression for the velocity as a function of time. So let's integrate v of t dt. That's going to be integral of mg over k e to the minus k over mt minus mg over k integrate with respect to t. So we get s of t is equal to mg over k, e to the minus k over mt. We're reversing the chain rule, or equivalently U substitution. We're letting u be equal to minus k over mt, and du is equal to minus k over m dt, U substitution. Because it's easy, we just do it in our head. So we're going to divide this by negative k over m. That's the same as multiplying by negative m over k. And integrating minus mg over k, that's just a constant. We get mg over k times t. Plus a constant of integration, we'll call that d. This is the height as a function of time. The only thing we need to solve for is to solve for the unknown constant d. And we're going to use the initial height of the object to solve for d. All right, so what we have is s of t is equal to minus m over k. We factor out minus m over k times mg divided by k, e to the minus k over mt plus gt plus d. Now the initial condition is that the object has a height of h at time 0. That means s of 0 is equal to h. That means when time is 0, when t equals 0, s is equal to h. So let's substitute those in and solve for the arbitrary constant of integration. So s of t, that's going to be h is equal to minus m over k times mg over k, e to the minus k over m times 0, so all of that is 0, plus g times 0, that's 0, plus d. So we get h is equal to minus m squared g over k squared plus d. So solving for d, d is equal to h plus m squared g divided by k squared. So let's substitute that back in, and we have the height as a function of t. So s of t is equal to minus m over k times mg divided by k, e to the minus k over m t plus gt plus d that we solve for, so that's plus h plus m squared g divided by k squared. So that's the height as a function of time. And now let's look at some theory, the physics behind the question. So what we have is basically we have the object that's here, and we chose the up direction to be positive and the down direction to be negative. So the force of air resistance is minus kV. Notice the sign, the minus in the front, because the object is falling. So the velocity, because we chose the up direction to be positive, as the object falls, the velocity is negative, since down is the negative direction. So force air resistance is equal to minus kV. Why is this a positive quantity? It's because the velocity is negative, and you have a double negative becomes a positive. So since velocity is negative, and we expect the force of air resistance to be pointing in the positive direction, because the force of air resistance opposes the falling motion of the object. Furthermore, we can see that when velocity is 0, as the object falls, just begins to fall, dv dt is equal to minus k over mv minus g, so the acceleration will just be equal to minus g, because the velocity is practically 0 in the beginning. And we expect that. So in the beginning, only gravity is acting on this object. But as the object falls, the force of air resistance starts to build up and oppose the motion of the object. So basically, dv dt is equal to minus g plus negative k over mv gets smaller in absolute value. Why does it get smaller? Because this is a negative quantity, minus g, but this part is a positive quantity. Even though there's a negative in the front, it's a positive quantity, because velocity is negative and you get double negative is a positive. So what happens is the acceleration gets smaller in absolute value because the force of air resistance is a positive quantity, and that's because minus k over mv is positive since velocity is negative. As t goes to infinity, the force of air resistance catches up with the force of gravity. It matches or equals the force of gravity is equal to mg, and acceleration of the mass becomes zero. It approaches zero, and the object falls down with constant velocity, because once the acceleration is zero, according to Newton's law, the object will fall down with constant velocity. That constant velocity, we call it the terminal velocity, which is minus mg divided by k. All right, thanks.